Well, howdy everybody, and let us continue our journey into chemistry. Okay, we are talking about thermochemistry, and we said thermochemistry is essentially about heat. We talked a little bit about energy, and last time we talked about delta H, right? We were talking about my change in enthalpy. I said I really don't care about enthalpy itself. I do care about change in enthalpy, that change in enthalpy at constant pressure is equal to my heat transfer. So that's important. The heat transfer between two bodies at a constant pressure situation is equal to my change in enthalpy. And from that, we said, hey, we could figure out change in enthalpy for reactions, which is the enthalpy of my products times their coefficients minus the enthalpy of my reactants times their coefficients, right, in the balanced chemical equation. And we said you can do all kinds of stuff with this, that if I have an enthalpy for a forward reaction, then that enthalpy is the same magnitude but different sign for the reverse reaction. And I have a reaction in which I double all my coefficients, then the delta H for that is twice the delta H of my original, right? And this looks kind of goofy, but that's the way this review is running today, right? Good. So if you want to see more on that, you can go back to the last lesson, right? And then we talked a little bit more. We talked about Hess's law, and we said, hey, if you have a reaction that's made out of steps, that I can show that it's a couple steps, and I have delta H for step 1 and delta H for step 2, then my total reaction is just, if I can add those steps up, then my delta H for that reaction is just delta H step 1 plus delta H step 2, right? Good. So that's Hess's law. And then we started talking about, hey, how do I determine delta H? And we got into the idea determining delta H and heat of reaction specifically. And we said one way to do that is something called calorimetry. Calorimetry. And we talked about coffee cup, highly technical term, right? Coffee cup calorimetry, and that's where I have a coffee cup and a reaction occurs in here, and it's in a solution, and all the heat from the reaction goes to the solution. So we say that Q of my solution, and we know this term well, is equal to the mass of my solution, C sub P of my solution, delta T of my solution, right? And then we say, hey, where did all that heat go? How did that heat get to the solution? Well, it all came from the reaction, or if it's reversed, went into the reaction. So Q of my reaction is same magnitude of Q of my solution, but they're just, one is gaining and one is losing, so they have a different sign. And then delta H for my reaction, what I'm really after, is just going to be Q of my reaction divided by usually moles of a reactant. They'll usually tell you, hey, I want it in terms of kilojoules per moles of hydrochloric acid. So I have to figure out the moles of the reactant and divide it into your Q, and that's how you get your delta H reaction. Great. Now today we want to go into something called heat of formation, and heat of formations are really great tools, and you'll find this out later today. We like heats of formation, but the first place to start is where? Heat of formation, right? And what is the heat of formation? It is, well, it's delta HF, right? Good. So that's heat of formation. And we always want to start with our definition, because if you understand the definition, you can really understand everything else about the concept. You can use that definition to do the math and to do the explanations and figure out the exceptions and so on. Definition, here we go. And words are important, remember that. So what is heat of formation? It is delta H of reaction, heat of reaction for the formation, and here we go, important words here. Formation of only one mole of compound from its, big word here, elements, okay, in their most stable form. Okay, and what we mean by that is stable form. Carbon has several stable forms. Carbon, diamond, but the most stable form of carbon is graphite. H is not the stable form of hydrogen. What is the stable form of hydrogen? H2, all my diatomics. I should be I2, and so forth. O, O2. That's what we mean by the most stable forms. The most stable form of magnesium is magnesium. Got it? In terms of an element. Good. So this is our definition, and it's an important one. We have to form 1 mole from its elements. Good. Now, we can add to that, which is standard heat of formation. And the standard heat of formation has standard HF and then a little 0 like that up there. Standard heat of formation. What this is the heat of formation at 1 atmosphere and 25 C. Okay? And so that just tells us this is a specific temperature and pressure. And why is that? Well, this is approximately room temperature and room pressure. And what's really cool about this is there are tables that we can use that have bunches of heats of formations, and I'll show you in just a minute how to use those. But let's go to our question. Consider the following reactions. Okay, I have a couple reactions. I have carbon monoxide going to carbon dioxide. I have hydrogen going to water, right? Which of these represents a standard enthalpy of formation or heat of formation? Good. Well, if it's standard, first what must be true? It must be at 25 Celsius and 1 atmosphere. Let's assume that's the case. Let's assume these are at 25 Celsius and 1 atmosphere. Now the question is, do these reactions represent heat of formation? Now what did we say heat of formation was? 1 mole from elements in their most stable form. Got it. So do I form 1 mole there? Yes, so we're still in the game. Do I form 1 mole there? No. Yoink. That one's done. Now let's go back. Am I forming it from its elements? Well, here's oxygen. That's cool. Here's carbon dioxide or carbon monoxide. Is that an element? Nope. Yoink. Neither one. We have our answer here is the empty set, right? Good. Let's move on. You guys can understand this. You guys do these 3 and bring me back. All right. Piece of cake. Oh, let's look at the first one. Do I form 1 mole? Yes, I do. Do I form it from its elements? Yes, I do. Do I form them from their most stable state? Sodium is O, the most stable form of oxygen. The answer would be no. Yoink. Survey says, we have to have O2, so it has to be 1/2 O2. We can use 1/2. Yes, you can use 1/2. It's not very common when we're doing normal stoichiometry, but in things like thermochem or in thermodynamics, we use 1/2 coefficients all the time. Good. Moving on. Let's look at my potassium. I have an element there, and that is a stable form, and that's a stable form, right? And what do I make here? I make 2 potassium chlorides. No good. That's wrong. Good. Moving on to the last one. I have carbon, and it's graphite. That's a stable form. Oxygen, O2. It's the most stable form. And I form what? 1 mole. Woohoo! Here we go. This is our winner chicken dinner right there. That represents a standard heat of formation as long as it's at 1 atmosphere and 25 degrees Celsius. Woohoo! Good. That's a neat piece of cake. Now let's talk about the fun stuff. Consider the complete combustion of 1 mole of propane gas, yeah? And that means if it's combustion, I'm reacting it with O2. And I'm going to form carbon dioxide and water. If it's water, that means it's H2O in what state? Liquid. Good. what is the standard heat of reaction for this reaction? Well, let's first write a reaction. Propane, what does propane? C, pro means what? 3 carbons. Ane means it is an alkane, and that means we're going to have CN H2N plus 2, right? So my N is 3, so C3H68. There we go. And it is gas, propane gas, plus oxygen gas is going to yield carbon dioxide gas plus water liquid, right? Good. And we want to know, what is delta H reaction here? Yeah. First thing we ought to do here is balance this. I have 3 carbons, 3. Okay, I think this will work. Yes. I have 3 carbons, so I have 3 carbons there. I have 8 hydrogens, so I need to have 4 hydrogens here. I have 3 times 2 is 6 plus 4 is 10, so 5. So it's 1, 5, 3, 4. There we go. So we have my balanced equation. Now, how is it that I'm going to get the standard, we'll put a little circle up here, standard heat of reaction? Well, here's the cool thing about my heats of formation is I told you there are tables, and so we can say, let's add another little bubble off of heat of formation, determining delta H reaction, standard heat of reaction from standard heat of formation data. Yes. Since we have this table here, then, and what's that table look like? It looks like that. Ooh, cool. See, we have a bunch of substances and we have a bunch of heats of formation at 298 K, which is 25 Celsius, right? Yeah, so we have these tables, and here's the process. It's a really easy process. Delta H of my reaction, standard heat of reaction, is going to be equal to M times the standard heat of formations for my products minus N, the standard heat of formation of my reactants. Good. And what are M and N? M is or are the coefficients on my product or products in balanced equation. And N is the coefficient, or R, coefficients on my reactant or reactants in the balanced equation. That equals my standard heat of reaction. That's all there is to it. It's beautiful. And here we go. Let's see how this is done. Right here. All right. So let's write out the reaction. I mean the equation. So what I would do is delta H reaction is equal to what? Well, products. Here are my products, yoink and yoink. So I have 3 moles, and so I'd have my standard heat of formation of CO2 plus 4 moles, and be careful, you got to watch states. States matter. 4 moles of my water, and it's liquid. Oops, sorry. Standard heat of formation of my water. We'll put this in a bracket. Minus, right, my reactants. Minus, big bracket, standard, 1 times, because there's a 1 here, my standard heat of formation, that's a funky 1, standard heat of formation of my propane, minus 5 times, standard heat of formation of my oxygen. And remember, states matter. All right, cool. Now, if I could only find these dogs, right? Guess what? Right there they are. No. Where's propane? Here's propane. Yeah, I like propane. What else? Water. Which one? Vapor or liquid? Water. And carbon dioxide gas. Yes, it's a gas, just like chemistry is always a gas, right? There we go. Woohoo! If only we had oxygen. Ay, caramba, I don't see oxygen. Do you see oxygen? The reason for that is most elements have standard heat of formations. Yoink. Have standard heats of formation equals 0. So if you don't see it in the table, you can safely assume that the element's standard heat of formation is null. Got it? All right, we can do this. Let's go back, plug and chug. Let's rewrite this and we'll put in our numbers. We're going to need some more space. Let's come down here. I have 3 times carbon dioxide. Let's look for carbon dioxide. Carbon dioxide right here. It's a negative 393.5 kilojoules per mole. Negative 393.5. Got it? Oops. Oh my. Negative 393.5 kilojoules per mole. Jawohl. Plus, we want to have, what, 4 times H2O. Let's go to, is that gas? That was liquid, right? Gotta go back, make sure I had the right one. Liquid. Yes, it was water. Liquid. Liquid. Here we go. Negative 285, negative 285.8. Negative 285.8 kilojoules per mole. Jawohl. And then we better put that in big gigantic brackets because we're going to have to subtract stuff. And we're going to subtract 1 times propane. Where is my propane? Right here. Negative 103.85. Negative 103.85 kilojoules per mole. And I said what? Oxygen, 5 times oxygen, but oxygen is 0. So that means that thing goes to 0. I don't have to worry about my oxygen. And I just have to be able to do some simple calculations. And you just have to, this is not difficult, but you can really mess up because of the negatives, right? You got negatives all over the place. So this might be a little tedious, but it's certainly not hard. So 3 times negative 393.5. Oops, I already made a mistake. 3 times 393.5 negative. Good. Plus 4 times 285.8 negative. Cool. And I get a negative 2,323. Okay, that makes some sense to me. Minus a negative, which is really a plus, 103.85. And my number here is I get a negative 2219.85 kilojoules per mole of reactant, right? Let's make sure that I do everything right. Everything looks right to me. Good, 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 good. Okay, so there we go. Now, let's watch our sig figs. Siggy figs. This guy could go to the 100th. This guy can go to the 10th. This guy can go to the 10th. My guess is I can only go to the 10th. So this is going to be equal to negative 2219.9 kilojoules. Now, you could say this is kilojoules as for this reaction. So this is kilojoules per mole of this specific reaction, per mole of the reaction as written, or you could say it's per mole of, since it's 1, it's per mole of what? Propane, or per 3 moles of carbon dioxide, or per 4 moles of water. So sometimes you'll see it just written as negative 2219.9 kilojoules, and that's an acceptable way to write it. Sometimes they'll write it this way. Sometimes they'll write it per mole of propane. It all depends, but this is a correct answer. Got it? Now, how much heat is generated by the combustion of 98.5 grams of propane? Okay, we're going back to our last lesson, right? We know this is per mole of reaction, and if we relate this to moles of propane, how many moles of propane did we have in that reaction? We had 1 mole of propane, so that would mean what? This is the same as negative 2219.9 kilojoules per mole of propane. Got it? Cool. Hey, just let's make sure I did my calculation right. I am always concerned about that when I do these things because I make mistakes. I want to go back and run my calculator one more time. 3 times 393 negative. I'm just going to take shortcuts. Plus 4 times 286 negative equals good. Plus 103 good, and I get negative. Okay, just that looks just about right. Have to go back and make sure everything is right. Now, I have 98.5 grams of propane. What do I want to do? I want to get moles of propane. So I'm going to take those grams of propane, 98.5, 98.5 grams times 1 mole per 3 times 12.01 plus 8 times 1.008 grams. And what do I get? Okay, 3 times 12.01 plus 8 times 1.008 equals, invert that, times 98.5. It looks like you get 2.233 moles of propane. And then I'm going to multiply that times 2219.9 negative, and I get negative 496.036 figs. Kilojoules are released when 98.5 grams of propane combust. Woohoo! All right, I think we have time for you to do one of these, and we'll call it a day. Got it? Here you go. Give it a shot. Get complete combustion of benzene. All right, bring me back when you're ready. Benzene. Okay, I like benzene. C6H6, it's a real cool structure, although I think it might be a little carcinogenic. That's not a good thing, but it still is kind of a cool molecule. And when you get to organic chem, you'll really learn to appreciate benzene. We form carbon dioxide gas and water. If it's water, that must mean it's liquid. We have to do what? Balance. I have 6 carbons, so I need to put a 6 there. I have 6 hydrogens. I need to put a 3 there. And so what do I have? I have 6, and 2 is 12, and 3 is 15. Oops, that doesn't work so well. Zoink, zoink. Let's try it again. And let's go with a deuce here. So now I have 12 carbons, and I have 12 hydrogens, and now I have 12 times 2 is 24, plus 6 is 30, so I have 15 oxygens. Good. So when I write out my equation for this, it's my standard heat of reaction is going to equal what? 12 times standard heat of formation of carbon dioxide plus 6 times the standard heat of formation of H2O, put that in a nice big bracket, minus 2 times the standard, oops, not there, 2 times the standard heat of formation of my benzene, minus 15 times the standard heat of formation of my oxygen. But we all know that the standard heat of oxygen is 0. Jawohl. Good. So let's go rewrite this 12 times. Let's go to our beautiful table. Whoops. Got a lot of writing on it. We need to clean that up so I can see what I'm doing. Na. Good. It was 12 times what? 12 times carbon dioxide. Carbon dioxide is, or CO2, carbon dioxide, negative 393.5. Negative 393.5 kilojoules per mole. Plus 6 times my water. Negative 285.8. Negative 285.8 kilojoules per mole. Right? Cool. Put this in big bracket. Big bracket. Minus what? 2 times standard heat of formation of my benzene. Benzene. Ooh, look at that. It is a 49. 49. Ooh, good. And it was liquid. Ooh, 49 kilojoules per mole. Was it just 49 or did we have a decimal point in there? Yeah, we did have a decimal point. We want to watch our sig figs, 49.0. Cool. There we go. Let's run the numbers. do, 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 do. 12 times 393.5 negative plus 6 times 285.8 negative. Cool. Minus 2 times a positive 49. And I get a big number like negative 6534.8 kilojoules per mole of reaction. Got it? And that would be what? It's also equal to negative 6534.8 kilojoules per how many moles of benzene? Well, per 2 moles of benzene, per 12 moles of carbon dioxide, per 6 moles of oxygen, per 15 moles of oxygen. But we'll write down per 2 moles of benzene. Got it? Yeah, cool. Let's run the numbers again. Make sure we're right. 12 times 393.5 negative plus 6 times 285.8 negative equals plus 2 times 49. Okay, good. I get a different number. Let's try that again. I made a mistake. 12 times 393.5 negative plus 6 times 285.8 negative. Oh, minus. That's where I made my mistake. 2 times 49. There we go. I get the same answer. So this is correct. Now, how much heat is generated by the combustion of 257 grams of benzene? So I need moles of benzene. 257.5 grams of C6H6 times 1 mole of C6H6 over 6 times 12.01. We're getting pretty good with these numbers now. 6 times 1.008, right? The molar masses. And what do I get then? I get 257.5. 257.5. Sometimes I can make my calculator work. Sometimes I make my tongue work too, but usually I'm having trouble getting both at the same time done. Divided by the quantity. 6 times 12.01 plus 6 times 1.008, close, 78.01, and I get roughly 3.296, 20 sig figs for 3.2967 moles, and that's a point, of benzene, C6H6. Okay, now be careful here. We want my total heat, right? We want to know the total heat released. Well, I have a negative 6534.8 kilojoules, but how many moles of benzene is that? That's per 2 moles of benzene. But how many moles of benzene do I really have? I really have 3.2967 moles of benzene. And now I can run the numbers, but don't forget about this 2 there. So I take 3.2967 times, recall 1, divided by 2, and my answer looks to be negative 10771. How many sig figs? Looks like 4 sig figs here. So it's negative 10770 kilojoules are released when 257 grams of methane are combusted. Woohoo! Hey, we're almost done with thermal chem. Next time we'll finish that. Have a good day.